Hello, and welcome back to the race. We're going to watch the points A, B, and C race around their respective tracks. The topic of this session is the angle swept out by the radius of the ellipse as theta increases at a constant rate from 0 to 360 degrees. It's time to give that angle a name. We will call it alpha. Here we have our blue circle, red ellipse, and green circle. Now let's take a look at the angles involved. I'll just stop there. Theta is the blue angle, which is 23 degrees. Alpha is the red angle, and you can barely see it, but alpha does not equal to theta. Depending on the shape of the ellipse, the difference will be more or less pronounced. Now let's observe what happens as it goes around. It will catch up and even get ahead. Notice that alpha is ahead, catching up again. Theta is ahead, and in the fourth quarter, alpha is ahead again. Here are some other examples of the relationship between alpha and theta. Notice that at 90 degrees, 180 degrees, 270 degrees, and back at 360 degrees, alpha and theta are equal. Now we want to express alpha in terms of theta. We will use the fact that the tangent of alpha is equal to the opposite over the adjacent. The opposite is the y-coordinate, of course, which is the height, and the adjacent is the x-coordinate, which is the length along the x-axis. So the tangent of theta is equal to 3 sine theta over 4 cosine theta, which equals 3/4 of tangent theta. You will recall from a previous session, we worked out that the coordinates of any point on the ellipse are given by 4 cosine theta, comma 3 sine theta. Now if we take the arctangent of each side, we will have that alpha is equal to the arctangent of 3/4 of the tangent of theta. Or in general terms, where B is the length of the semi-minor axis and A is the length of the semi-major axis, alpha is equal to the arctangent of B over A times the tangent of theta. The next session will examine how fast is alpha increasing in terms of degrees per second as theta increases at a constant rate. See you next time.